Еще раз всем добрый вечер. Первый доклад выступает Хасан Фудайл. Хасан, вам слово.
Yes, I'm here. Can you hear me?
Yes, we hear.
Okay. Start the class.
Yes, you can start.
Okay. So, can you see the screen?
Yes.
Okay. Our topic today is speaker verification approaches using neural network-based architectures. In this presentation today, we will take a brief introduction to speaker verification, the general architecture of solution used for speaker verification task. We have two based solutions, we have probabilistic based solutions and neural network based solutions. And I wanted to talk on both of them, as that probabilistic based solution is the base of neural network based solution. And at the end, we'll have a comparison between multiple solutions that have been applied in this in the task of speaker verification. The presentation today is not about the work that I already have done, but it's a review about a work that is done in the field of speaker verification as a new field that I'm searching in. Speaker verification is the process of making decision whether the speaker is genuine or not, depending on his voice. One of the main uses of speaker verification is with the voice assistants in smartphones, smart TVs, and cars. It's used to authorize user for commands that needs either personal information or for actions that needs special authority, for example, for payment or something else. To register the voice of the user, system asks user to record multiple audios that will be reference audios for verification. The general architecture is starts from registration. In the registration, we are extracting the features of the speaker that has registered, and for each time we are trying to verify the user. We have the following process. The process could be divided into 4 stages. The first stage is pre-processing. It's in this stage we are processing the audio files for noise filtering, spectrogram extraction, or some other methods that transfer voice to frequency domain and manipulate the voice in a frequency domain. Feature extraction, which is the main part in this presentation, it's the task of extracting features of the speaker. Multiple concepts of features were developed, such as GMM, Gaussian mixture model, I vector, X vector, and many other approaches. These concepts share the idea of extracting a vector of real values, which are the features of the speaker, while the difference between them is in the extracting tools. The third stage is similarity score. It's the process of comparing the features of the speaker with the feature of the target speaker. Usually, and the most common similarity score used for speaker verification is cosine score. The last stage is decision making. It's to accept or reject the speaker, whether he's the genuine speaker or not. Starting from the probabilistic based solutions, GMM, Gaussian mixture model. It's a trainable probabilistic method that modifies, as you can see in this in the figure below. The process is as follows. First of all, we have the audio. We are applying Fourier transform, taking the magnitude of the voice. After that, multiplying this magnitude with GMM and taking the logarithm. At the output, we have the probability of that this this record or this audio is a speech or not. The method modifies the parameters of GMM to maximize the likelihood of the training data, so that it will maximize the likelihood that all training data that we have are speech data. GMM is usually trained using speech from many speakers, and this in this case it's called UBM, that it's trained for multiple speakers. So the task of GMM is that it's trained for speech detection. How GMM could be used for speaker verification? After training the GMM for speech detection, we are training this model more times using the speech of the target speaker, so that the speech of the likelihood of the speech of the target speaker will be higher than the likelihood of speech of other speakers. In this case, if we if we passed an audio for some speaker to both the original UBM model and the modified UBM model using the target speaker, the likelihood of the target speaker will be bigger. That likelihood of the speaker will be bigger than the likelihood of normal UBM model if the speaker is the target speaker that we trained for. Another probabilistic solution is I vector. It's also a trainable probabilistic method that maximize the probability of speech records of the target speaker. The general equation of I vector is M, the big M equal to small m plus T multiplied by W, where small m is speaker independent supervector. It's generated by combining multiple UBM vectors It's speaker independent because it's trained for multiple speakers, not trained for this for the target speaker. While MBIG is a speaker dependent supervector. T is low rank total variability matrix that we generate it randomly and training it to generate I vector, and W is the vector of that is I vector, that what we are searching for. The process here is that we have this M speaker dependent supervector. We are training using the audios of the target speaker. During the training process, the two arrays T and W are modified so that the probability is maximized. So we can say that the main concept of I vector is to find the low rank vector that represents the features of speaker's voice, which means to reduce the dimension of speaker dependent supervector, which is big M. So the two solutions, the two probabilistic solutions are correlated. Let's move to the neural network based solutions. The first one is X vector. In X vector, the features extracted using a deep neural network. This deep neural network is trained for task of speaker classification. The input of this neural network is the MFCC of audios. It takes this MFCC features, process it, and at the output of the deep neural network, we have the probability that this audio belongs to each of the speakers that we have. The architecture of this deep neural network is could be split into 3 levels: the frame level, statistics level, and sentence level. Frame level is consists of multiple time delay neural networks. The difference in the number of these networks make different versions of X vector. Statistical level, it's just an pooling layer, while sentence level is multiple dense layers. And so, except for the last layer in sentence level, each layer could be could be an X vector embedding. So in this, as you can see in this example architecture, we have 2 different dense layers that could be used and X vector embeddings. D vector. The structure of D vector extraction model is also a DNN, but it consists of locally connected layer with ReLU activation. It's the first layer. After that, multiple fully connected layers with ReLU activation. And at the end, we have a fully connected layer with linear activation. This deep neural network takes an audio frame. It's a pure audio frame with fixed length. And the output is a vector of real values that represents speaker. D-Victor is created by Google in 2015, and after that they adapted this method to using LSTM neural networks, but they proved that D-Victor is more useful for diarization tasks, but for speaker verification, it's not that. The results of using D-Victor in speaker verification is still behind the state of the art. The using of ResNet for speaker verification. First of all, ResNet, it's a classical neural network used as a backbone for many computer vision tasks. In speaker verification problem, ResNet is used as feature extractor that extracts voice features from the spectrogram of the audio. So the input of ResNet is a spectrogram. The ResNet is trained for the task of speaker classification. The embedding could be extracted from the Breno limit layer, which is the layer before the last layer. For the
Hassan, sorry, you have no time left. Please conclude your presentation.
Yes, this is the last slide. For comparison between different approaches, the best approach that used X-Victor has achieved about 6.3% of equal error rate, while the use of D-Victor achieved the best use of D-Victor achieved 3.34% of equal error rate, while the use of ResNet achieved 0.69% of equal error rate. The best solution until now is the solution that used ResNet. And thanks for listening. Sorry for taking much time.
Thank you. The first opponent is Ali Moaz.
Yes, I'm here. At the beginning, I would like to thank Fudai for this presentation. My first question would be about how do we deal with the noise in the voice records, and well, how we deal with some records, for example, that have multiple speakers in the background. For example, sometimes it's very difficult to identify the main speaker. So what approaches do you use, for example, to deal with these records, with such records?
Okay, so for the first question about the noise, so about dealing with noise, it depends on the pre-processing process. As I explained, that in the pre-processing process, each solution could choose the most convenient pre-processing approach for filtering the noise, as long as most of them are transferring the voice to the frequency domain. So to remove the noise, it's just to remove the frequencies of higher and low frequency. And for the second part of question about multiple users, multiple speakers in the audio, if in case that the audio contains only one voice, and the other voices are it's lower in the level. Its level is lower, so it's in the background. So it will be filtered as noise, as long as most of the training approaches, are training the data with noise. So the feature extractor will learn how to remove the noise from the input audio. But in case that there are two speakers with the same voice level, so this task couldn't be solved by speaker verification, because it's another task that it's responsible to detect the speaker change events, and this task is responsible for splitting the voice in case it includes multiple speakers. But if the speakers are in the background, so this problem could be solved.
Okay, thank you. And another question is about how many examples in average we need to train from each user. We need to train the model for speaker verification.
Usually, the system asks for multiple audios. Most cases, they are asking for from 3 up to 6 records from the user. And much of the time, in voice assistant system, they are asking the user to record the keyword. It's called keyword because they are using this keyword to activate the voice assistant system. So they are asking the user to record this keyword multiple times.
Okay. And another related question to this topic is how do we combine the features extracted from one user's records?
You mean if we that we have multiple audios for the same user?
Yeah, for example, the system has asked the one user to, for example, record multiple. For example, you said 3 or 5 records. How do we combine these records to extract the features that represent some user?
Okay. In most researches, the most common way to combine features from multiple audios is to get the average of these features. But in the recent researches, there are some researchers that tried to implement a self-attention neural network for this purpose, and this approach reduced the equal error rate in general.
Okay, understood. And could you please go back to the slide with X vector?
Ali, sorry, you already asked 3 questions, so it's enough, and we need to ask other questions.
Okay, thank you for that.
Thank you, Mars.
Schneider Lasse.
Yeah.
Please ask your questions.
Yeah. First, I would like to thank you for the presentation. And I would like to know, how do you guarantee that during the training, you have an equal or representative part of the population, so that you have also like a good mix of like male persons and women and old people, young people?
Sorry, I can't hear you clearly. Could you please repeat the question?
How do you guarantee during the training that you have a like good representation of different people, so that you have like male people in the training and women and older people and younger people?
About your question, it depends on the data set used for training. The most common data set that is used for training is VoxClip 1 and VoxClip 2. It's actually a data set that is generated from multiple YouTube videos. They created a pipeline to process these videos, detect speaker using face detection and face recognition methods, and they generated this data set that contains information about which user is speaking, and that the data set contains users of multiple genders, multiple multiple ages, and we can say that the data is variant. The number of audios in this data is more than 1 million audio. It's for about 1,500 speakers or something like that. I'm not the accurate. I don't remember the accurate number of speakers. So the choose of dataset is responsible for variety of speakers.
Okay, thank you. And how is the equal error rate, like EER, how is it determined?
Your question is how to determine equal error rate.
Yeah.
Yes. So in general, in speaker verification, there's two common errors. Let's go back to the first, to the general approach where we are making the decision. So we have this threshold that we can modify. So this threshold is to define the minimum distance between two speakers to identify that they are the same. So in speaker verification, we have two errors. Either we have the two audios for the same speaker, but we rejected them, or the two audios for different speakers and we accepted them. The first one is called false accept error, and the second one is false reject. So the equal error rate is the error rate when the false accept rate is equal to the false reject rate. That's how equal error rate is calculated.
Okay, thank you. And then I have a comment. Can you go to the last slide? You maybe it would make sense. I think that you don't like computed the equal error rate for the data sets them yourself. So I think it would make sense to like put the sources behind them from where you get these data. Like,
you mean to make a reference for the papers from where I took this? Sorry, I forgot for this. I can I can modify it in the presentation and upload the presentation again today. And thank you for your comment.
Thank you, Lasse.
Thank you, Schneider.
Yes, and the last opponent is Bushaev Alexei. Алексей, вы здесь? Алексея, видимо, нет. Okay, the last opponent is not here. Can I ask a question from myself?
Yes.
As I understand, the first two lines in this table are related to the feature extraction method. And the last one, ResNet, is end-to-end system of speaker verification.
No, also ResNet is feature extractor method.
Okay, then what algorithms are used for classification or for determination of threshold?
Determination of threshold is used depending on the requirements of error rate. So if we want the false accept error rate to be as small as possible, we may reduce it. We may reduce the threshold so that to reduce the false accept error rate. But in this case, we will increase the false reject rate. So defining the threshold is it depends on the requirements of application that we are using. So, for example, if we are using authorization for high-level authorization, like for payment issues or something like that, so the threshold is determined to make the false accept rate as small as possible. For example, 0.001, while accept that the false reject is 2 or 3%, for example.
So developer defines the threshold manually, and then we look at the results and correct it. Yes?
No, it's not. It's just to first of all define the requirements. For example, to take the best. For example, if the requirements is to make the false accept error less than 0.001. So we can identify the threshold, the best threshold that make this the highest threshold that makes false accept ratio is less than 0.001. So it depends on the requirements exactly.
Okay, I see. Thank you for your presentation.
Thank you for listening.
Переходим к следующему.
Any other questions?
I think we don't have time for other questions. We need to move forward.
Thank you.